Shall we start? Okay. So, thanks everyone for coming to this slot today. We are going to address a few different topics related to P2P today. Again, Ahmad mentioned Amit and myself, but thanks to Ahmad for his collaboration on this. My name is Bhaskar Chinni. I am a product manager at Broadcom. I manage time synchronization and telemetry solutions in the networking business unit. And my colleague today, Amit Oren, who is the distinguished engineer, he is a guru of P2P, and he will address P2P TC. So, I will start with TC and BC, and then Amit will explain the P2P TC, because these are the three key aspects that are deployed today in data center networks and service provider networks, right. So, when it comes to TC, stands for transparent clock, it is a very lightweight kind of time synchronization that can be enabled. It is easy to achieve because it can go through network nodes that are not P2P aware, right. Typically, the endpoints synchronize directly with the grandmaster, and that means the grandmaster need to scale to support all the endpoints. The packets of course go through the network in all the switches in a hop by hop manner, and wherever the P2P aware switch is there, it updates the correction field of that TC message, so that the end to end, this is what we call, right, transparent clock end to end. The endpoint gets all the updates in a cumulative manner. So, this does not require a lot of changes and a lot of software or hardware configuration changes, and it is already deployed at Meta, right, and it is good for achieving typically some sub-microsecond kind of accuracy, like hundreds of 400, 500 types of accuracy, but cannot be used for a class C type of service which is required for 5G networks, let us say, right. And the more important thing is, here we are at OCP, it is all about openness, and the switch abstract interface SI is the interface that provides API to the higher level applications, and Broadcom is supporting this SI initiative for all the features including P2P. So, these are the APIs that we support for end to end TC, which are already in use by our customers. Basically, essentially enabling all ports TC or port by port at TC. Then boundary clock. Boundary clock is a bit more sophisticated mechanism, because it requires some additional P2P software, right, because in boundary clock the messages are traversed in a hop by hop manner, right, because if you take a switch, on one end it acts like a receiver to the grandmaster, on the other side it acts like a master to the endpoints, or it could be another BC, right. So, that is why it is called boundary clock. So, the P2P messages are terminated and then re-originated. That is why I am showing here in a hop by hop manner. And sure, there is a bit of additional complexity with BC compared to TC, but it gives you higher accuracy, it can scale better because all the endpoints are not directly having sessions with the grandmaster. So, and this is the recommended model for service provider networks, where you need a higher accuracy, class B, class C, all that kind of stuff, right. And again, Broadcom supports both one step and two step, and we are actually supporting P2P4L, also known as Linux P2P, where you could use that stack and enable it on Broadcom silicon. So, you do not have to have your own P2P stack or server, and we already supporting this for both data center network deployments as well as service provider deployments. And again, SI support, right, because if you think of a sonic type of operating systems, it cannot be used unless there is a SI support. So, this SI support we have, to trap the P2P packets, because the packets need to be terminated, and then we also have basically adding P2P trap and removing P2P trap, as well as enabling whether it is a 5 timestamp or not. So all those API are already enabled and then released in the commercial software that we published. Then peer-to-peer TC, Amit will explain from here. Amit?
Yeah, so it's well known, right, that P2P provides the option of implementation option to use either end-to-end delay measurement or peer-to-peer delay measurement. And end-to-end is probably much more commonly implemented because all the telecom profiles use end-to-end delay measurement. We in Broadcom are advocating to seriously consider the advantages of peer-to-peer delay measurement for several reasons. We can talk about a couple of them today. One of them is the scalability of peer-to-peer. If we look at an end-to-end deployment, then we can see that the sync flow can take advantage of multicasting, so that in terms of the workload on the master, sync is not a big deal. But in an end-to-end delay measurement, each endpoint has a unicast flow all the way up to the master to perform the delay measurement, and that can present a scalability issue. In contrast, in peer-to-peer delay measurement, the nodes perform the delay measurement not all the way to the master, but rather to their peers. And then they figure out the end-to-end delay by adding the segments or the delay of each segment of the path from the master to the slave. And that's how it's figured out. But in terms of the workload on the master, he only has to worry about his immediate peers, not all the endpoints in the network. And that offers significant scalability advantages as that are not present in end-to-end measurement. Another important consequence of using peer-to-peer delay measurement is that, again, if every node in the network implements P2P, then the peer-to-peer measurement is basically across one hop, and then we can use that for cable length measurement. Basically, two nodes, if they're interconnected by fiber or something, we can actually measure the length of that by using this peer-to-peer delay measurement mechanism. Can you? The peer-to-peer delay again measures across a single hop, and you can isolate the different components of the end-to-end path and measure each segment separately. And that can be done actually very accurately. We have some measurements that we conducted that we can share today. And so before we actually go into the measurements themselves, it's important to understand what exactly is being measured when we do peer-to-peer delay measurement. And it's important to understand that what we're measuring is not just the cable, but it's timestamper to timestamper, the delay between timestamper on one node to the timestamper on the other node. So it includes not just the cable, but additional logic or semiconductor delays that are present. And in fact, you can see in the table that we have here that where we conducted peer-to-peer delay measurements by connecting a delay generator, and we can see that in each case we incremented the delay between the participating nodes by 2,000 nanoseconds. And you can see, right, that even in the case of zero-length cable, we still have delay, and that is the reason is, again, that we're measuring from timestamper to timestamper, so even if the cable is zero length, there is still delay in the system. But you can actually see that as we increment the delay between the nodes, every step that we took was 2,000 nanoseconds. You can actually see the delta between the measured delays that is almost accurate to the nanosecond, right? I mean, you can see that as I go from 2 nanoseconds to 4, so 2 microseconds to 4 microseconds, right? The measured delay increases by 2,000 almost to the nanosecond. Again, when I go from 4 microseconds to 6, you can see that, that this can be done extremely accurately. But again, what we're measuring here is actually delay, and the way that we conducted this measurement is by using a delay generator. We did not actually modify the length of anything. So these delay measurements have to be then converted. If you're interested in cable length measurement, then these have to be converted. And so any kind of simple linear model or polynomial regression is probably can give you excellent results where the zero length is sort of the intercept, and then the slope. In a fiber, you would expect the slope to be kind of 5 nanoseconds per meter, roughly, but you can actually achieve very good measurements by probably applying fitting some model, linear model probably can work very well here. So it's also important to remember that I don't need the nodes to be synchronized to anything. I don't need the sync flow. I don't need any kind of master present to be able to achieve that kind of accuracy, right? I mean, the nodes have their very cheap Ethernet class oscillator, and we're still able to achieve these kind of accuracies without any kind of master or any kind of sync flow in the system. These are just two nodes that implement peer-to-peer delay measurement without any master present or any sync flow that is present in the system. And it's still, even if they're not synchronized or not frequency synchronized, each one has its own oscillator, we're still able to achieve very high accuracies in measuring delay. You wanna?
Yeah, so basically, where do we go from here, right? Like, we want to enable the consumption or the deployment of PTP easier across all the deployments, right? And as I said, we are enabling Linux PTP, and our customers have already deployed it. So let's contribute to this Linux PTP project so that it becomes more and more feature rich, as well as scales well for various use cases. Then call to action, again, let's collaborate. We are contributing to SAI. If you have any requirement that you need to be addressed in SAI Sonic deployments supported by Broadcom in Broadcom networks, please reach out to us. We'll be happy to support. SAI supports these deployments, and also let's deploy these boundary clock and peer-to-peer TC, because end-to-end is, as I said, is very popular. But I think peer-to-peer TC also has a very good number of use cases, as I explained. And of course, Amit went through the details of link delay measurement, which is a key requirement for hyperscalers, and more and more enterprises also leveraging it. With that, we'll open up for any questions. Thank you.